I would like to thank the organizer for having invited me to this interesting workshop. The topic for today's presentation is the earliest bombardment history of the Earth. I would like to get started defining a few terms that will be used throughout this talk for the benefit of those that are not familiar with the topic. So what we are trying to do here is understand the earliest collisional history of the Earth. I have a timeline at the center of this chart. This is very schematic, but it shows that the time zero is when the Earth starts forming. That is the condensation on the first solids in the protoplanetary disk, so-called calcium and aluminum rich inclusion, CAIs. Then there is a period of time, perhaps up to 90 million years or so, in which the Earth was formed. That's the primary accretion of the Earth. After that, we have a gigantic collision that resulted into the formation of the Moon, and that is, by definition, the starting of the late accretion. So the late accretion is what happened to the Earth after the formation of the Moon. Now, in terms of geological history of the Earth, this encompasses the Hadean and early Archean. How do we study this early period in the evolution of the Earth? Well, we could rely on planetary accretion models, but those are largely uncertain due to lack of solid constraints. And also, of course, if you want to look at geological history of the Earth, the very fact that we lack rocks from Hadean is a major source of uncertainties. Luckily enough, the Moon comes to the rescue. And now we swapped the position of the Moon and the Earth in an image to the left. The Moon was there, as we see in the timeline, during the late accretion by definition. And so let's look at the Moon. Now, that is interesting for a number of reasons. Well, first of all, there's lots of impact craters on the Moon, and craters, of course, are a proxy for collisions. It basically, the Moon provides a snapshot of 4.5 billion years or so of collisional evolution. It is least affected by geological evolution, unlike the Earth. And more importantly, we also have samples from the Moon that can be used to produce an absolute model for the impact flux throughout time. Now, before we go into the details, I also would like to show in a nice way a dramatic difference between the Earth and the Moon. There are only 13 craters known larger than 50 kilometers on Earth. Famously, we can see Chicxulub and Rutherford, which is one of the oldest. It's about 2 billion years old. And now compare that with what we see on the Moon. We have 1,500 craters larger than 50 kilometers. That's in order, 2 orders of magnitudes more than we have on Earth. And furthermore, the surface area of the Earth, it's much larger than the Moon. In fact, the Moon area, surface area, is about the same of Africa. So now imagine all those craters crammed into Africa. So quite a remarkable view. So ideally, we would like to know the ages of those craters so that we can build together an impact flux model. So how do we do that? Well, luckily enough, we have samples from the Moon, as we said, thanks to the exploration of the Apollo and Lunar missions. We have samples from various regions in the near side. Those orange numbers superposed to the near side of the Moon and the Langdon sides of the Apollo missions. I also indicate some of the most notable impact structures and basins in the near sides, and some of which we do have age constraints as indicated. Altogether, we have about 500 kilograms of lunar rocks, and now we can study those rocks in order to reconstruct the collisional history of the Moon. And here is where the concept of the lunar cataclysm, which is very important in planetary science, was born. And so I would like to spend a few words on that. And in fact, I would like to show the original plot by Terra et al. In 1974, in which a synthesis of radiometric ages of lunar rocks was first published, and here is where the concept of the lunar cataclysm was first proposed. Now, this is really the plot from the paper, and it's amazing to see in the top part that basically we didn't have any knowledge of the impact flux. You see, there is a straight line there, meaning no knowledge at all pre-Apollo. But as soon as we start getting data from the Apollo and Lunar missions, it was obvious that the impact flux around 4 billion years ago must have been much higher than it is today. And in fact, in the plot at the bottom, there is an indication of a strong surge or spike in the impact flux as measured by lots and lots of argon and other radiochronometer ages around 3.9 billion years ago. And that is, in a sense, the source of the lunar cataclysm. Sometimes we refer to this event as a terminal cataclysm, or in more recent times, the late heavy bombardment. But these are the same events. Now, this is a very long story, and it's marginal to my talk today. I want to say that empirical evidence for the lunar cataclysm has been strongly debated, and it is still debated. There are supporters and detractors, and here I have some reference that you can go in if you are interested in this debate. But what's important for us today is talk a little bit about what are the processes that could regulate the impact flux into the Earth-Moon system. And now I would like to make an analogy. Let's imagine the solar system. It's like a snow globe, right? So if you let the snow globe there on the table quiet, nothing is happening. There is no snow flying around, meaning in our analogy, there are a few collisions. But now all of a sudden you take the snow globe and you shake it. And so you have the snow flying around, and again, that would imply in our analogy, lots and lots of collisions on the Earth and the Moon as well. And now you wait a little bit and things settle down, and again, the impact flux is at its minimum. And so, you know, the impact flux in the Earth-Moon system is really sensitive to these shaking events that we might have. And how do we do a shaking event in the solar system? We do that through a dynamical instability. This is shown here as an example in a simulation, and there are different models as well. So this is just one example, basically. What we see in panel A is the configuration of the giant planets in those circles, and outside the giant planets, we have a sea of planetesimal. You can think about this as a primordial comet, and here I'm not showing the Earth because we'll be, you know, very close to the Sun in this chart, but the same thing would apply to the inner planets as well. Now, the important thing to realize is that when our solar system formed, those planets probably were in a very compact configurations. As time goes by, we see panel B, the planets' orbits start to drift a little bit, and so eventually the giant planets got caught into an unstable situation that triggered a scattering event, as we see in panel C. Now the orbits of the planets are much wider, and also the planetesimals or the primordial comets have been destabilized. And after a while, we end up to panel D, in which the system, the planetesimal are gone, and we now have planets on current orbits. Now, why do we need something like this? There is plenty of evidence in the structure of the solar system that we must have had an instability of this kind early on. We see that in the planet orbits. We see that in the asteroids in the Kuiper belt. But really, the question is when that it happened. There are different camps. It could have happened very early, maybe tens of millions of years after the formation, and that would imply that perhaps the Earth was not even there. So it would not have seen this surge in the impact flux triggered by the instability. Or perhaps that happened late, up to 500 million years after formation, in which case this could have affected the Earth. And again, I have reference here for those that want to investigate this aspect a little bit more. But let's now bring it down to the Moon, what the Moon would have seen. What this plot is a summary plot now that shows the latest models that we have. On the y-axis, we have a number of craters larger than 1 kilometer per unit surface as a function of time. The dots and symbols that you see over here are actual data from the Moon obtained by measuring a number of craters on a terrain for which we know the age, thanks to the Apollo lunar missions, and there are different compilations. And finally, we have two curves. And those correspond to the latest model. We have a model with an early instability in blue and a model with a late instability in red. Now, you compare those two curves, there are certainly differences, particularly early on, and early stability is higher than the late instability, meaning more collisions. But altogether, these differences are not really dramatic. So this is where we stand for the moon. Now, we have established, we have a model for the moon. We want to use this model throughout the rest of the talk to study what happened to the Earth. And for doing that, I will rely on the red curve here, the late instability, which is a little bit more conservative in the number of total collisions that we expect. And this is shown in this chart. Now we're talking about the Earth here. On the y-axis, we have the mass accreted by the Earth in bins of 25 million years. Collisions are stochastic. So here I have 50 different Monte Carlo simulations to give you a sense of variability. And on to the right-hand y-axis, we have the equivalent projectile size. And now we have finally a model for the Earth. And this is good because now we can play with it. But first, we need to stop and ask ourselves a question: is there anything better that can be done to verify if this model even makes sense for the Earth? Do we have constraints? And the answer is yes, in the forms of highly siderophile elements. These are elements such as ruthenium, osmium, iridium, and so on. And the interesting aspect is that these elements are being highly siderophile, have the tendency to go to the core of the Earth, and so very little of them should be left behind in the mantle, but we find those elements in significant concentration. The reason is why. What this plot shows on the y-axis is the ratio, the abundance of those elements with respect to a standard. In this case, is a chondritic material of the type Ci, most pristine materials we find in the solar system. And the common understanding of this plot is that the distribution of these elements in the Earth it's relatively flat on this plot somehow. There is errors and there is variation, but geochemists will say, and this is a relatively flat distribution. It's not far off from what we find in the meteorites as indicated. And so this is an indication that these elements have been added to the mantle of the Earth during the late accretion. And if you do a mass balance, it takes 0.5% of an Earth mass to deliver these elements. Now, 0.5% of an Earth mass, it's not much, you would think. However, if you imagine to spread that mass at the top of the surface, you will end up with a layer which is about 50 kilometers thick. So if you are concerned about the evolution of the Earth, this is an important contribution, as I will argue, for the rest of this talk. And so now we can put that constraint in. This is the same plot as before, but now it's color-coded. And you see that there is a bunch of simulations, those in red, that deliver a total mass that is compatible with the HSC's constraint. And so those are about 20 to 40% of our simulation. So this is a successful model in the way that not only explain data, lunar data, but also explain the amount of HSCs in the terrestrial mantle. Interesting enough, most of the mass on this evolution has been delivered by a very few large impactors, as we'll comment in a minute. And so now it's about time to stop for a second and ask a question: does the late versus early instability matter for the scope of this workshop? And my answer to that is not really. It doesn't really matter if the instability was late or early. In all cases, there were plenty of collisions on the Hadean Earth. And so that must have been an important contribution to understanding the prebiotic evolution of the early Earth. And so we can sort of, for a moment, ignore the long-lasting debate of whether there was an LHB and focus really on understanding what the effect of the collisions was back then. And this is what I'll try to do in the rest of the talk. Now, we can switch gear to part two. I want to give a couple of examples of how collisions could have been important, and I want to talk about metals and Schnapp's elements. What we see now is a large-scale SPH high-resolution simulation of a 3,000-kilometer impactor striking the Earth. Now, we said that most of the mass during the late accretion was delivered by large guys. And so this is one such example. I have two plots on the left. I'm going to show you the effects of mixing. And so, for instance, we are tracking the core of the impactor in white. That is where the metal is going to be, and also the HSCs. And in the right-hand panel, we are tracking the temperature. As the simulation goes by, you'll see there is lots of things that takes place. There is mixing, there is disruption of the Earth. But what's important now to realize is that if you look at the panel on to the left, you see those white dots. Well, those are core for particles from the impactor, and we'll see some of those are embedded in the mantle of the Earth, and some others are flying around and near the surface. So here's the direct delivery to near surface environment of iron, nickel, and many other elements that could have been important for prebiotic processes. On the right-hand side, we see the temperature evolution. Notice that most of the surface is strongly heated, perhaps even molten. And also there is a large fraction of the mantle in this specific collision that's been strongly heated and molten. And so this has an important consequences for the stability of volatile elements such as schnapps, because first of all, they can be delivered by these massive collisions, but also they can be mobilized due to melting and outgassing, and so to near surface environment again. So here there is an important consequence. And now I want to show you a little bit more details about the mixing, right? So here is a slightly different SPH simulation, a smaller impactor, but notice now in brown, we are tracking the core of the impactor. And again, you see there are large clumps of core, hundreds or tens of particles or so that basically go down to the base of the mantle. Well, when that happens, the metals and the HSE's concentration of the impactor are not going to be delivered to the mantle. And plus, there are lots of particles close to the surface, as we said earlier. Now, why this is important? Because we realize that if the impactor is differentiated, that the efficiency, the delivery of HSEs is not 100% efficient. In other words, in order to explain the amount of HSEs that we find in terrestrial rocks, we in fact need to increase the total mass, perhaps up to a factor of 2 to 5. And so this would imply even more collisions that we are that have been traditionally assumed up to this point. Now, a little bit about carbon, nitrogen, and sulfur. There are interesting observations here. Well, first of all, carbon, nitrogen, and sulfur are generally siderophile at pressure and temperature conditions relevant to core formation. So you would expect that those elements to be somewhat depleted in the mantle of the Earth. What's more important is that the carbon, it's more siderophile than nitrogen and sulfur. And so if you look at the ratio carbon over nitrogen, carbon over sulfur, you would expect those to be lower because most of the carbon goes into the core. However, that's not what we find. The plot here shows that, for instance, the C/N ratio, it's higher. It's actually higher than what we find in many meteorites, meaning it's superchondritic. So even if we started with the mantle of the Earth, which is bulk chondritic, it would end up, because of core formation, in something that's lower than the meteorites. Instead, the Earth, it's actually higher. The C/N and C/S ratio are higher. So how do we explain this? We said that the late accretion traditionally consider addition of chondritic material to the mantle of the Earth, but that wouldn't do the trick for these reasons. And so perhaps the idea is that differentiated impactors may have played a role. And this has actually been investigated by a researcher that found that indeed that could be the case. What they have done is consider the partitioning of carbon, nitrogen, and sulfur in impactors of different sizes, and then imagine to add the mantle of that impactor to the mantle of the Earth. And what the plot shows here is their final result, in which you have the mass of impactor with respect to the mass of the Earth to the y-axis, and here on the x-axis there is the metal over silicates ratio of the impactor. Now, if you have something bulk chondritic, you would be sort of around 0.3, so this sort of central part of the plot. And what the color region is where they find a solution, meaning that if you were to add an impactor with this mass, with this ratio of metal over silicate, you would potentially explain the C/N and C/S ratio in the mantle of the Earth, and as a function of the bulk carbon content of the impactor itself. The conclusion of this work is that you need an impactor close in size to Mars. Now that is perhaps what it took to form the moon. So this could be coincide with the moon forming event. However, there is an interesting aspect in this computation. The authors did not consider equilibration between projectile core and mantle of the Earth, but we saw from previous simulation that may have been an important process. So if you allow for a little bit of equilibration, then you end up with a smaller mass, as indicated. So 5% of equilibration between the core of the impactor and the mantle of the Earth will bring you down to much smaller mass. Perhaps this is now compatible with late accretion impactor. So it is possible that late collision somehow played an important role in establishing carbon, nitrogen, and sulfur content for the Earth. More work is needed in this regard. Let's now talk a little bit about part 3, surface evolution. When you have massive collisions of the early Earth, there is melting. Here I have a couple of SPH simulation, 600 kilometer impactor or 100 kilometer impactor. The color coding give you the melt fraction, and each panel is split in half. You see the impactor here, half of it, and this where all the molten material is coming from, and on the right hand it's the final distribution after crater formation, so to speak. What's important to realize is that the amount of melt that is produced in these large scale collisions is huge, and in fact, because melt is buoyant, you will expect that this melt to erupt at the surface. So now let's assume that all this melt is spread at the surface with a 3 kilometer thickness. Then we can ask what is the size of this lava lake that is produced. Turns out the diameter, it's about 20 to 30 times the impactor size. So in other words, if you have a 100 kilometer impactor, you may end up with a lava lake at the surface of the order of 2,000, 3,000 kilometers in diameter. Let's see the effect of that. Now we have a simulation, it's the Monte Carlo. The color give you the timing information. Every circle here on this chart is either a crater if the impact is small, or if the impact is large, where we have this effect of lava lake production, then we have the size of that lava lake. We can go by, and as the time goes by, you'll notice there is a great deal of effect. So when you see a picture like this, I think the image, it's kind of clear that all those collisions early on must have had an important role in establishing habitable conditions and triggering prebiotic processes on the early Earth. We just need to find out precisely what happened. There is a question related to that whether or not impacts were able to sterilize the Earth altogether, and the answer is no. Let's see how that is the case. What you see here are snapshots of simulations in which we actually track the temporal evolution of the crust. So every time there is a collision, there is thermal pulse, and then we simulate how that cools over time. Now, each square on this diagram is actually the entire surface of the Earth. And so there are large volume of crust that are eaten by collisions, there is no doubt. If you do sort of a cumulative effect of all collisions, the crust has been reprocessed and eaten several times over. However, at any given time, there is always a significant fraction of the surface of the Earth that is not affected by collisions. And so I don't think that collisions would represent a bottleneck, in other words, for early life. We can see that also in a slightly different way. Here we define habitable volumes. This is a very simple thing to do. We just rely on temperature, right? Based on the mesophiles, thermophiles, and hyperthermophile temperature ranges as indicated. So we simply compute the volume of crust within those temperature ranges. And we track how that evolves over time. The dashed line over here is the maximum volume that is habitable based on these conditions. And notice, because the delta T is the same, the volume is the same for all the regions. And the curves gives you the evolutions once we superposed a Monte Carlo collisional evolution of the Earth. So clearly, the volume habitable increases over time, and by 3.5, basically collisions have very little effect. However, you will notice that at any given time, there is a significant fraction of the Earth, of the crust that is habitable. And so again, the collisions did not limit the potential for early life on Earth. A related question is, how about ocean stability? Well, it is estimated that 500 kilometers is what it takes to vaporize completely the oceans, assuming today's volume. And so we can compute with the model stochastically what is the latest time in which we can have that ocean vaporization event. And it turns out that it's close to 4.3. So even in terms of stability of the oceans, there could, there is no measure effect after 4.3 billion years ago. And again, so the early Hadean could have been habitable. A related question is about the dry land on early Earth. Dry land, it's important because, for instance, for some prebiotic scenarios, could be a way to have little water concentrating elements and molecules and dry wet cycles and so on. But the question is, did we have a dry land on the early end? Based on geophysical models, it seems perhaps unlikely because several regions, maybe the oceans were much more massive than they are today, absence of plate tectonics and other reasons. It has been suggested that perhaps hotspot volcanoes could have pierced through the oceans and established small-scale dry land, but there is another process. And the other process I would like to talk about is the role of collisions again. Just look at this picture, which is a wonderful picture of Oriental Basin on the moon, and you get right away a sense of the tremendous topography that has been generated by these collisions. And in fact, we did a very simple simulation. This is very preliminary, but now we can take one of our Monte Carlo simulation, turn that into a topography map. So what you see here is the results of all the craters that excavate and redistribute ejecta around and trying to track all of that evolution of topography. We end up with excursion in terms of topography of the order of tens of kilometers. And so potentially collisions could have been also an engine of topography formation of the early Earth, which is kind of rather interesting to think about. And now we are hopefully trying to do more simulations in this. So hopefully we'll have more results soon. Let me talk briefly about an aspect of atmospheric evolution. The others will talk about early atmosphere on the early Earth during this workshop, but there is an aspect which is important that I would like to mention. When you have a massive collisions on the early Earth, you would expect to vaporize rock and create a transient a silicate-rich atmosphere. This could be even up, strongly heated up to 1,000 Kelvin. The point here is that this is a very transient atmosphere. Everything will rain down on a time scale perhaps of 1,000 years. And so these are sort of what I call transient effect of a collisions. But there are much longer time scale effect that could be important. Remember that we mentioned that there's large gigantic lava lakes that are producing collisions. Well, it's going to take some time for them to get in place at the surface because this is geophysical time scale, perhaps up to a million years or so. But once you have all that melt established at the surface, you would expect outgassing. And so you could outgas CO2 and other species. So here's the aspect that we want to look at, those long-term outgassing. I'm not concerned today on this topic, on this talk about the transient effect. Here is a simulation that shows what would happen based on our assessment. We have CO2 on the left and SO2 on the right. Now we have a couple of curves. This is the cumulative output, outgassed by the lava lakes as a function of time. This is an incremental plot. So every dot here is what happened in 25 million years. We have two curves because we want to consider just the outgassing from terrestrial rocks or even adding contribution from the impactor. And as you see, there is a substantial amount of CO2 that could have been outgassed by this process. Now, compare with the dashed curve, that is what it takes to offset the faint young sun. In other words, to have warm surface conditions. And as you'll see, there is potentially enough CO2 in the system to do that. On the right hand, we see sulfur. Sulfur is interesting because perhaps there was little sulfur in the mantle of the Earth early on. However, you'll see that when you consider the impactor, there is a boost in the amount of sulfur, and that's because impactors are typically sulfur rich. And so this could be a nice way to add a significant amount of sulfurs to the surface. Now, I will have to say that this is just looking at the total budget outgassed. Of course, when it comes to the CO2, CO2 is not stable in the atmosphere. There's a weathering cycle. And so we did that, look into that more closely. What you see here is um, two plots. On the left, we have assuming a drawdown timescale for the CO2 of 1 million year that's compatible with the Earth. It's rather fast. And what you see now, it's every time there is a collision, there is a spike of CO2 due to the outgassing, but that goes down quickly because of the weathering. And so here could be a situation in which there was high level of CO2, and then low level, high and low every time there was a collision. Something like perhaps repeated episodes of snowball Earth, potentially. However, a slightly longer drawdown time scale, which is compatible with what people think about the Hadean, could have sustained high level of CO2 throughout the Hadean and earlier Archean. So with that, I would like to go to the conclusion. There are a number of future directions that needed to be investigated better. It's really try to understand what the roles of impacts are, and there is a great deal of implications. For instance, in terms of delivery of nutrients to the near surface, we have discussed about a possible contribution to generate dry land. Of course, collisions would also trigger a great deal of mineralogical evolution for the crust. There are effects onto the transient effect to the atmosphere, but also long-lasting effect. There is the shear delivery of Schnapp's elements and mobilization of those elements. And one other thing that I did not have time to cover, it's the role of impacts generated hydrothermal system in triggering interesting chemistry early on. And finally, there are also implications for organic synthesis and tectonic evolution of the early Earth. So all of this, some of this is left for future work. With that, I'll stop here. There are the conclusions here is that the most intense phase of the bombardment was done by 3.5 billion years ago. Impacts were a major geological process during the Hadean Earth, and they could have triggered all sorts of interesting things, from delivery of key elements for prebiotic chemistry and altering the tectonic regime of the Earth, topography, and so on and so forth. But the issue here that I would like to make clear is that now there is little concern that the impacts took place on the early Earth. There is no model that would say otherwise. So the question now is how those impacts shaped the evolution of the Hadean Earth. And with that, I'll stop here. Thank you.